Hello and welcome back. Differentiation from first principles. Today, the product rule. A lot of limits, and I have put some results here that we're going to take for granted. Let me first of all tell you what these results are saying if you cannot see them, because I wrote them in green unknowingly. It says the limit of, if you have the limit of two functions, f of x and g of x, as we take it towards a particular quantity, let's say c, as x tends to c, I put plus or minus there, but I missed the plus or minus here. So it's actually the sum or difference of the two limits, assuming of course that the two limits exist. And the same thing is true actually for product. So if we have a product of two functions and we take the limit as x tends to some quantity, real quantity c, then it's the same as the product of the two limits, assuming the two limits exist. In fact, it works for division as long as of course the limit on the denominator is non-zero. Okay, the level of this is probably undergrad / enrichment / a little bit of further maths. It's not the kind of standard stuff that you're likely to get in an exam, but it's actually quite straightforward. It's quite a straightforward proof once you see the very initial steps. So let's have a look first of all how we're going to prove the validity of the product rule by using, of course, the definition of the derivative. So of course the definition of the derivative, I'm going to write that up here. F dash of x is of course the limit as h tends to 0, f of x plus h minus f of x, the whole thing divided by h. Okay, so this is the definition of the derivative. So we're trying to find dy by dx if y is the product of two functions, f of x times g of x. So what we're going to do, not that we need to, but let's say we call the product of these two functions, another function of course of x, call it the h of x. So we're going to apply the definition of the derivative. So my dy by dx, which of course is the same as h dash of x, because I called it h, is just this thing here but in h. So that is the limit as h goes to 0 of h of x plus h. It's a bit bizarre, h, but we will lose that h. I just realized actually that my choice of function, fgh, and then I have h of course in as my little thing in there that needs to go to 0. It's a little bit bizarre. H of x over h, but luckily on the next line this h function will disappear, because of course h is f of x g of x. So on my next line I'm going to say, okay, that's the same as the limit as h goes to 0. Now what is h of x plus h? Of course f of x plus h times g of x plus h minus h of x, of course f of x times g of x, the whole thing over h. Okay, so far so good. It's the next step now that is actually quite tough to actually think of it, and this is what I was looking. If you had to give me this particular proof, before I look it up, I'll say, okay, I don't know what to do next now. I cannot think of anything sensible. But the next step is quite clever. Is the following. We're going to manipulate this numerator as follows. So a very, very, very long fraction line. Okay, let's write this f of x plus h times the g of x plus h. And we're going to add and subtract an identical quantity, so I will not change, of course, the numerator or the limit. So we're going to say, we're going to let's say add f of, actually let's say subtract first, it's probably better. We're going to subtract f of x plus h times g of x, and of course in order to balance it we need to add of course exactly the same quantity, so that's f of x plus h times the g of x. So these two of course cancel each other out, and still my fraction line is not long enough, because of course I got at the end minus my f of x times my g of x, close limit, and let's not forget the denominator. Okay, why did we do that? It's because we are going to group, okay, the terms in twos, in pairs, and then split the limit in an additive and then into a multiplicative sense. I'm going to actually show these steps slowly and detailed so we can all follow what is going on. So far so good. It's exactly the same thing, just written with these extra red bits in the middle. So out of those two terms, quite clearly there's a common factor of f of x plus h, so I'm going to factorize it. So f of x plus h, and it's going to leave me inside there g of x plus h minus g of x, which looks again like some kind of g dash of x if it was over h and everything else. So this is going to be now still my big fraction line all the way to the end, and I dealt with those two, and out of those two terms quite clearly they have a common factor, g of x. So I'm going to factorize the g of x to the front, and what I will be left inside, I will be left with an f of x plus h minus an f of x, which again is a similar looking term. It looks like some part of the derivative if we had it over h, and of course the whole thing is over h. Next we're going to use the property of the limit that says if you have an addition in the middle, this property here, we can actually split it to individual limits. And because a lot of rubbing, a lot of writing obviously of exactly the same thing just for the split, I'm going to cheat here and I'm going to split my fraction to 2 bits. So there's my 2 fractions, and take the h over each of them individually. I hope we're all happy with that. So I have now I've done this split in there, which of course will move me into 2 separate limits as h goes to 0. F of x plus h I'm just merely copying this quantity into a single limit, and of course I have another separate limit now, limit as x goes to 0. If I had left a little bit of a bigger gap, I could have actually squeezed limit in there and saved myself a line. Unfortunately, I didn't plan it very well, and I have to be writing again tediously the same line just to split. Okay, so far so good. Next we're going to use, of course, the property of limits that says if we have 2 functions inside the limit, we can, in a multiplicative sense, we can actually split it into 2 limits multiplied each other. Where are these 2 things now? We got a limit here and we have a multiplication. What about this h? This h can either go f of x plus h over h times that, or it can go f of x plus h times that. It is up to us where we want to put this over h with, and of course it should be obvious that where we want it is of course to be part of this term, because of course in a separate limit this is actually the definition of a derivative. So I'm going to write it as the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of this quantity here, so g of x plus h minus g of x, the whole thing over h. I hope we can all squeeze it into, and I don't run out of board. How are we going to split this one? Of course, is the g of x times this quantity as a single lump. So plus, I put there x tends to 0. It shouldn't be x is equal to 0. I just realized h goes to 0. Little typo there. Limit as h goes to 0, g of x times the limit as h goes to 0, and I have just about squeezable in there f of x plus h. I hope it's visible on the video, that's all, over h. Very long. And if we look now let's make some room just in case we cannot see the bottom of the board and see what we got left. The time it takes me to rub off the board, we should be able to actually see what that produces. So, okay, let's look at this limit first of all. The limit as h goes to 0 of f of x plus h. Well, if that goes to 0, that will clearly become f of x. Okay, this now is the definition of g dash of x. It's just that bit up there, but for g's. Okay, so that's times g dash of x plus the limit as h goes to 0 of g of x. Well, that has not even got a h in there, it's independent of h. So of course that will return us a g of x. And of course the very last thing, we should recognize it, is of course f dash of x, which of course is what we expect and what is required of us to prove. I thought it was quite neat. That step, that balancing, adding and subtracting was quite tricky to see. You need to have seen it before, and once you've done that, after that the proof of course flows. I hope you enjoyed it. I hope you found it educational. Join me again very, very soon. Who's laughing now?